Hey everyone, in this video I want to explore the new Azure Gateway Load Balancer, a brand new option for integrating network virtual appliances with our regular workloads. As always, if this is useful, please like, subscribe, comment and share and hit that bell icon to get notified of new updates. I have some workload that I want to make available. I can think about, okay, I could, for example, just have some kind of resources. Generally, we have multiple resources for scale, for resiliency. And the way I make those available in that resilient fashion is I'll put them behind a load balancer. So I can think about, okay, I've got my load balancer here. I have a backend set that points to them. And this load balancer would have that public IP. Now, another option, absolutely, is I can just have a resource, and that resource can have an instance level public IP. But we don't really like doing that. We'll give that a frowny face, because now it's talking directly to this instance. I'm not getting those kind of scale resiliencies. That's not generally something we want to do, but definitely is an option. So now I have this service, I'm offering it, but I want to add in some kind of network capability. This could be a file, it could be monitoring, packet analytics, inline distributed denial of service checking, traffic mirroring, a whole bunch of different things. So what I now want to do is I say, okay, I want to put in some kind of network virtual appliance. If I think about those, hey, I have my network virtual appliance that has all those different types of functions, as we kind of talked about. But how do we do that? How do I actually integrate those things? I want to put it into this line. So the way this has to work today, and it's not really the ideal, is, well, this. And imagine I have multiple. Again, those same arguments for kind of resiliency. I might have multiple network virtual appliances. So once again, we have this idea of the load balancer. So the load balancer in front of the NVAs has that public IP. Well, then it goes through here and would then send the traffic to this, which no longer has a public IP. It would just have a private IP. Because the flow of traffic is going to come into this public, go through the NVA, go to the private. But if this is stateful, the traffic has to go back that way. And the next hop can't be this public IP load balancer. So you have to add another load balancer on the inside, which has got kind of a private IP. So it's an internal, so traffic can go back out. But then you get into all sorts of problems, because it's a different load balancer for the sort of ingress and egress path. If I go through the same load balancer, I get symmetry. I'm guaranteed to hit the same backend member. If I'm using a different load balancer, that goes away. And so we get into this ugly situation where generally I could only have one active, and then I could have passive, but then I lose a whole bunch of the benefits. So really not super keen. I did a whole video where I talked about highly available NVAs and how you can kind of manage that and fix that solution. So if we think about this new Azure Gateway Load Balancer, it addresses these problems. So what I now think about is, I'm going to kind of forget about that part of the picture. So what we're now going to create is this brand new Gateway Load Balancer instance. So I'm going to come over here. And it's just a load balancer, but this time we're going to create it of this kind of gateway load balancer. Now this is internal, it's using a private IP address. It only uses HA ports, so those rules that we would use with NVAs in the past, we're not doing individual rules per port. This is actually designed for network virtual appliances. Again, it's only internal. And then obviously we have the backend instances. So once again, now my backend instances are those kind of NVAs. So I have my NVA, N number of NVAs. These could be virtual machines. Could be a virtual machine scale set. Obviously, virtual machine scale sets are nice because as they get added and removed, it will automatically register itself with the gateway load balancer and be part of that set. Now, one thing you can do here is these NVAs, yes, they're a back-end pull to this new gateway load balancer. And they're all active-active. I don't have to have passive because there's only one load balancer that the kind of customer traffic is going to be going through. But if I think about management of the NVAs, one option you can have, and again, this is completely optional, but I may actually have kind of a management load balancer here. So these can actually be part of multiple back-end pulls because then my management could kind of throw through here to actually do things specific to the NVAs in terms of their actual management. Again, this is completely optional. I don't have to have this kind of second public kind of load balancer to actually do management on the NVA. So that completely optional, don't have to do that. But my normal operation is now my NVAs will sit behind this new type of gateway load balancer. And we can see that quickly. So if I jump over, and if I just go to regular load balancers over here, and I hit create, what we can see here is if I change the type here to internal, then we get this option for gateway. So we get this brand new type of option right here. And that's really just the key part of this. So when I use this gateway load balancer, now it's going to give me these new options and these new types of interactions that I'm actually going to be leveraging. So that's the key point. It's just a load balancer, but normally we have kind of the standard and the basic. Well, if it's internal, I can also now pick this gateway. So now I'm adding these NVAs behind it. So this is now currently just a completely separate load balancer. So how does that relate to this path coming in? Well, I go back to the idea now that I forget about trying to put something in the line. Before this had a public IP, I go back to that. Once again, this is now a public IP. It's a regular public load balancer going in the front of my resources. But what we're going to do, and this is the clever part now, is we have this concept of chaining. So what I can do is I'm now going to create a chain from that standard public load balancer to the gateway load balancer. I can also chain from an instance level public IP. So I have choices there. So what I'm doing is I'm just leaving those workloads as they were, but now in the load balancer, I have this option, hey, I want to chain to an instance of a gateway load balancer. And of course, the gateway load balancer has these NVAs doing those tasks like packet inspection, firewall duties, all those different capabilities. And we can go and see that. So if I just go back super quickly and go back to just my load balancing, and I go and look at a regular load balancer I have here, now right now we can see it has kind of a front-end configuration. It has an IP address. So there's 20.88, which I'm running here. I can just refresh and it goes to a couple of backends. But as part of that front-end configuration, we have this nice little option of a gateway load balancer, which I have configured. I've got it pointing to the gateway load balancer I have created, and we're going to look in more detail at. Now I can turn that off. I can set that to none, save, it's submitting that deployment, and it's just going to carry on once that's finished. So that's done. My website still runs. Likewise, I'm going to go and add that chain back. So now it's going back through my gateway load balancer. And again, my website just carries on working. Likewise, I can actually do that to that instance level public IP. If I go and look at a network interface card, and I just go and pick one of these, for example, if we look at the IP configuration, we can actually see once again here we have this option to add the gateway load balancer. So yes, I can do it on load balancers. I can also do it on instance level public IP configurations. But we really prefer the idea of using a load balancer just because the benefits load balancers bring to our workload. So yes, I can chain it to an instance level public IP if that's what I have, but ideally we're using just a regular standard load balancer. But now, hey, I can just go and chain in that gateway load balancer to bring me the various benefits. Now, when I think about these services, what's really happening here, this NVA is a provider of the service. So this is kind of my provider. You'll hear that terminology. And all of these, well, these are essentially consumers. They are consuming that service, that NVA service that I'm making available through this. Now, when I think about this gateway load balancer, what's really powerful here is there's all Azure uses GRE behind the scenes as part of its software-defined networking. This gateway load balancer, well, it can actually be completely different networks. In fact, when I think about what can be different, it can be a different VNet, and it doesn't have to be peered. It can be a different subscription. It can be a different region. Now, different region, you want to be careful with latency. If I go and stick this in a different region, well, realize it's going to bounce back and forth. So that's probably not something I typically would want to do. But it could even be a different Azure AD tenant. So that I don't have to peer these networks together. I can chain my load balancer to a gateway load balancer in a different VNet, a different subscription, different Azure AD tenant without any peering relationship between the VNets. It's that GRE magic and the Azure software-defined networking that's just going to make that work. And the ability to have this really isolated way is super useful because if you think about ordinarily the groups responsible for our network virtual appliances will not be the same people responsible for applications. So that ability to put this under a completely separate set of sort of constructs from the application owners is huge. And that's going to be really, really powerful when we think about that. So now if I think about what's going to happen, okay, so this has just the public IP, and I can really think that, okay, well, the traffic is going to come in. It's going to go through here. It will be sent to the internal gateway load balancer, where it will go through kind of that regular rendezvous hash algorithm. It will pick one. So the traffic would go to it. It will do whatever filtering. Now, if it was a firewall, if it was an inline distributed denial of service and it drops it, well, then it's just going to drop the packets. It doesn't go anywhere. But assuming now it says, okay, this is okay, well, it would come back. It will go to the load balancer. And then again, it does its kind of hashing and it will send it to one of them. And likewise, the return path. Okay, it will go back through here. It will send it through. Because that rendezvous hash, it will go to the same appliance. And then it will come back. And then it would go out. So it's going to work in both directions, even if the traffic is actually just sourced from this end. So remember, a standard load balancer, I might have NAT rules for actual outbound traffic. So the same thing would happen on that as well. It's going out, it would get sent to the gateway load balancer, it would go through those checks, and then it would go out over to the internet. So all of those same things would apply no matter kind of which way that traffic is going. So a huge thing about this is symmetric. I'm guaranteed, even though this is active, because there's kind of this one load balancer here, I'm always going to go to the same NVA for a particular combination of source and destination IPs. It's never going to go to a different one. So I'm not going to, if I have statefulness in these NVAs, it's going to carry on working. That's guaranteed as part of this. That's kind of the whole point. There's also no routing changes required. In these scenarios in the past with this, I had to have those kind of UDRs and force things through. There's none of that. There's no UDRs, there's no custom stuff I'm having to do. Again, it's just going to work. So it's going to guarantee that flow symmetry. I remove any of those complications. If I think about networking and I think about what's happening with this chaining, this is a true bump in the wire, i.e., both the source and the destinations have no idea that these are part of the path. There's nothing changed about the source IP or the destination IP. It is completely transparent to the source and destination of this actual workload. So it's kind of some magic going on there. Now, when we talk about magic, then, we're not changing the source IP, we're not changing the destination IP. How is this actually functioning? And what's some of the configuration we have to do to make this work between the gateway load balancer and the NVAs? Now, I do want to stress, I'm walking through what is required. Most of the time, what's going to happen is you're going to use one of these NVAs from like the Azure Marketplace, and it'll have a template, and it will deploy the NVAs, it will deploy the gateway load balancer. You don't need to know any of this. But I think it's kind of fun to understand how this is actually working. So the way this is actually working is it's actually using something called VxLan. So the whole point of VxLan is it's this virtual extensible LAN. I'm going to go into some more details. But the traffic between the gateway load balancer and the NVAs is encapsulated with VxLan. Now, what that encapsulation really looks like is you can think about, I have the original packet and all the things that are part of the packet, the IP headers, the TCP, UDP, whatever that was, the payload, that's the original packet. Now, what gets added to this is you get a VNI. A VxLan network identifier, also called a VxLan segment identifier, segment ID. So it's some unique, like in a VLAN, you have a VLAN tag. I think there's like 4,096. Well, I can have up to 16 million of these VNIs. And then this whole thing is wrapped in UDP. And this is what enables us to, and then obviously there's the regular IP, Ethernet gets put on top of all of that. So this VNI is that VxLan network ID. So that's what identifies a particular flow, a particular tunnel of this traffic. So this is how we can send the original packet without changing the source and destination between the gateway load balancer and these NVAs. So these NVAs, they have to understand VxLan. Also realize we are adding stuff onto the packet. So if I think about the regular Azure MTU, this is a 1500, it starts fragmenting, I think, at 1400. So what actually happens is the MTU of these is typically set to 4000. So it's larger to make sure it can handle these extra bits. It's nowhere close to 4000. It adds a little bit, but you'll see these NVAs will typically set at a higher MTU to make sure I can handle this additional stuff that's added to the actual packet. So the key point here, we're sending these without any alterations to that original packet. This encapsulation lets us actually do that. Now, because this gateway load balancer is on the same VNet as the NVAs, there's no routing involved there. There's nothing else I have to do. And then the NVAs, well, they receive this, they decapsulate it, so they can look at the original packet, look at the source IP, the destination IP, the payload, make their decisions, and then re-encapsulate it to send it back to the gateway load balancer. Now, for that encapsulation, if you actually go and look at the gateway load balancer configuration, we configure two tunnels. So I drew this single line. That single line is representing, hey, there's these back-end set members as part of the back-end pool that the gateway load balancer is talking to. But what actually happens is there are two tunnels established between the gateway load balancer and every single NVA. So I could think about, well, yes, absolutely, there's this kind of tunnel, there's an internal tunnel, but there's also established, we'll draw this in a different color, pick light green, there's also an external tunnel. So we get two tunnels. Now, each of these tunnels uses a separate VNI. Remember, like that VxLan tag ID and a separate port. So we're going to see those different values for it. And what happens is on the gateway load balancer, I configure those values for the internal and external tunnel, and they have to match the tunnels I configure on the NVAs. So I've said internal and I've said external. So the internal tunnel, well, that's traffic to and from the NVA to essentially the application, to the customer service. Really kind of that trusted set of connections. The external tunnel is used for traffic to and from the internet. So that's why we have the two tunnels. I can think about internal, I'm talking to the customer service. External, I'm talking to and from the internet. So that's why we have two tunnels there. So they have different ports. I can't use the default 4789 port. And again, it's going to correspond to my load balancer configuration. So let's quickly go and look at that. And then we're actually going to go and look at the NVA as well. So if I jump over and look at my load balancer again, look at my back-end pool, we can see here, well, this is configured. Now, we can see a number of interesting things. Firstly, the protocol is VxLan. My type is internal and external. And then here you can see I've configured the UDP port and the identifier. So that identifier is that VxLan network ID. So I've got 800 for my internal, 801 for my external. So I can see those in action right there. Now, if I jump over for a second, so I have this up and running. So this is obviously my gateway load balancer. And I do have this Linux NVA in my environment. Now I'm faking it. This is not a real NVA. It's essentially just bridging the traffic. But it bridges it, it turns it around so I can show it to you. So if I quickly look at my tunnel interface list, we see that same information. We can see the identifier here is 800 for my internal and 801 for my external, and then 10800 and 10801 for my UDP ports. Now what this is an SSH connection to that little NVA I've created. So if I do an IP link show VxLan 800, so that's my internal, well, what we can see is I have the matching configuration. So right here, you can see my VxLan is 800 and my destination port is 10800. So that's matching what I configured on the gateway load balancer, and you have to have that. If I look at my 801, my external, well here, my VxLan ID is 801, and my destination port is 10801. And that's really the key parts. I mean, that's what you have to do to make this function. Now, super quickly, this is what I did to actually get this up and running. So I created just a regular Ubuntu Linux virtual machine. You can see here I'm running some commands to update it, upgrade some of the components. I'm then setting IP forwarding equals 1, so it will do IP forwarding. I'm disabling the built-in firewall. And then what I want to do is I want to set some commands each time this VM reboots. And the way you do that in Linux is you basically create a service. As you can see here, I create a new service file. I'm doing this sudo vim. And then I'm creating a service called NVA network.service. And the content of that file is just this. Essentially, all I'm going to do is use bash to call this NVA-VNI setup script. And then that script, I define my variables. So you can see those same variables. Now, the only thing you'll customize is this IP. That is my gateway load balancer private IP. So you'd probably want to change that. I set the MTU to 4000. And then I just create those tunnel interfaces. So I create the internal tunnel, the external tunnel, and then I bridge them. And then I've got the commands here to make these basically executable and services. And then you'd reboot. And then these will be there every time you kind of start up the machine. And then I've got some commands to actually go and view the various pieces of information. So like I can do an IPA, and you can see, yep, there are my 2 VxLan connections right there. So that's the flow, that's the configuration I have in my actual environment. And what you'll actually see is that, yeah, the traffic is just going to flow through these as I actually start doing various things. Now, before I get to that, if I think about therefore, okay, so that's my dummy NVA. It's really not doing anything. It's bridging the traffic, but it shows it's in that kind of path. Again, it works in either direction. So, hey, if I'm coming from the internet, yes, it kind of comes in to the chain, over the external tunnel, cleaned, filtered, goes back over the internal tunnel to the customer service. If I'm going this way, okay, goes out over here, goes to the internal tunnel to the NVAs, goes out over the external tunnel, out over to the internet. Obviously, remember, there's still health probes going on here. It's only sending traffic to the healthy NVA. So maybe I've got something running in the NVAs, like I can do a HTTP S443. In my case, I'm just using TCP22, i.e. is SSH responding. So it's the regular, I need something to probe to make sure they're healthy before I'm sending traffic to it. From a network security group perspective, there's nothing special about this. Remember, this is on the same VNet as the NVAs. There's already a built-in, hey, allow traffic from the Azure load balancer. You'll see that on any kind of NSG. If I was to jump over really quickly, I mean, there's just basically nothing special you have to do. If I go and look at any network security group, so here I'll just go and look at this NSG. And all we're really looking at is there's this default rule here for allow the Azure load balancer. So nothing special I have to do. It's just there by default, and that's going to let it do that work to actually go and do the kind of health checking. Now, obviously, if you added your own NSGs and were locking things down, we need to make sure you open up the ports to allow, for example, those UDP traffic to actually go through. Remember, we specify those various UDP ports there. But that's really all there is to it, and it's just going to kind of work. So on my environment, when I'm refreshing that page, every time I'm refreshing it, well, the traffic is going through those NVAs. If we try and look at it, I can see if I can refresh it. So if I'm over here, so here if we look at the stats on kind of that interface, you can actually see the kind of the packets over here, the bytes or the traffic actually going through. So if I just jump over and hit refresh a whole bunch of times, trying to get some traffic through, if I look at it again, we'll see kind of that traffic has gone up. So we can see the actual packets has increased, kind of just proving that that data is actually going through it. It's not, there we go. So we can kind of see everything that's going through. There's the values. So it's hitting the NVA. Again, this is a tiny, tiny website, so we're not seeing a whole bunch of traffic, but it's actually the numbers are increasing as it's going through because it's hitting that NVA as part of the path. So just a super simple kind of view of that kind of in action. So that's kind of the key point. Now, I think there's 11 partners today that have kind of worked with the product group that have these solutions out there. But Again, there's nothing particularly special about this. It's just VxLan. You could have your own custom solutions in here. You could write things. The NVA might handle the decapsulation and encapsulation of the VxLan, or as I did in my example, I'm just using the Linux to do that, and then the NVA wouldn't even particularly have to care. I can chain multiple NVAs in this. Maybe they're doing different functions. I can do that. For the most part, you're not going to know about this. The NVA providers are going to start switching from using this old style that calls them pain with active passive and symmetric flows to, hey, great, I don't have to worry about that anymore. I can just create my appliance, and now you can just chain it to multiple different load balancers or instance level public IPs. So it's kind of a really cool, nice thing. Shout out to Anavi, Jose, Daniel, and Heather. We bounced some emails back and forth because I'm not a Linux expert at all. So trying to create this dummy NVA and trying to learn how to just even start the commands automatically at reboot. Where's the autoexec.bat in Linux? I'll tell you. So we were working some things out. So it was actually a lot of fun. But that's it. I mean, the whole point, this is really going to make life a lot better now for those network virtual appliances. I'm not having to mess around, hey, giving it some public IP and having to do UDRs. Hey, I just create my network virtual appliance environment with its own gateway load balancer. And the things that want to use it, hey, I just chain to its regular standard public load balancer or even an instance level public IP, and I'm done. Again, complete isolation. Doesn't have to be peered, different VNet, different sub, different even Azure AD tenant. Again, the region I'd be careful with from a latency perspective of doing that. But there you go. I hope this was useful. As always, a lot of work goes into preparing for these, so I really would appreciate a like and a subscription. But until next time, take care.